Have you ever stopped to think about what's actually going on inside the power cord of your laptop, or really any device you plug into the wall? Well, today, we're going to pull back the curtain on that invisible force that powers, well, pretty much our entire world. We're talking about the alternating current circuit, or AC for short. Okay, so at the most basic level, electricity really has two main personalities. On one end, you've got direct current, or DC. Think of it like a river flowing in one steady, straight direction. That's the kind of power you get from a battery. But then there's the stuff in our walls, and it's a whole different beast. That's alternating current, or AC. Instead of a straight line, it's constantly changing direction, oscillating back and forth in this beautiful, rhythmic wave. So you might be asking, why AC? Why did this back-and-forth current win the famous current wars and become the standard all over the globe? Well, it really boils down to three huge advantages. First, and this is the big one, its voltage is super easy to change. You can use a transformer to bump it way up for sending it efficiently over hundreds of miles, and then step it right back down so it's safe to use in our homes. This makes it way more cost-effective. Plus, the machines that run on it, AC motors, are just simpler and tougher than their DC counterparts. Less to break, less maintenance. It was just a smarter system. All right, so to really wrap our heads around AC, we've got to learn how to read its signature wave. It's kind of like learning to read music. Once you get what the notes mean, the whole symphony of electricity just clicks. So when you look at an AC wave, there are three key things that define it. First, you've got the peak value. Pretty straightforward. That's the absolute highest point the wave hits. Then there's frequency, which is just how many full cycles, how many back and forths, happen every single second. Here in North America, that's 60 times a second, or 60 hertz. In Europe and other places, it's 50. And last, there's the instantaneous value, which is just what the voltage is at any single specific moment in time. But here's where it gets interesting. That peak value, it's not actually the number that tells us how much work the electricity can do. For that, we need something called the RMS value. It stands for root mean square. Now, the key takeaway here is that RMS is the effective value. It's the practical, real-world number. It tells you what the DC equivalent would be to get the same amount of power, the same amount of heat. It's the true workhorse of AC. Right, so when you see 120 volts on an appliance in the US or 220 volts in Europe, guess what? That's not the peak. That is the RMS value. That's the real effective power you're working with. Kind of cool, right? Okay, so now that we know what the wave looks like, let's see what happens when it runs into the three basic building blocks of any electronic circuit. We're talking resistors, inductors, and capacitors, and trust me, each one has its own very distinct personality. First up, we've got the simple resistor. Its job is exactly what it sounds like. It just resists the flow. So when you send an AC wave through it, the voltage and the current are like perfect dance partners. They rise together, fall together, and switch directions at the exact same time. They're perfectly in sync, or what engineers call in phase. Next, let's talk about the inductor. An inductor is really just a coil of wire, but it does something fascinating. It hates change. It stores energy in a magnetic field, and that creates a sort of electrical inertia. So when the voltage tries to change direction, the current is always a little sluggish. It takes a moment to catch up. The result? The current wave always lags behind the voltage wave, specifically by 90 degrees. And then you have the capacitor, which is, you guessed it, the complete opposite of the inductor. A capacitor stores energy in an electric field, and unlike the inductor, it loves change. It's like an eager beaver, charging and discharging super quickly. It's always trying to jump the gun on the voltage, and because of this, the current wave actually leads the voltage wave, again, by 90 degrees. Okay, so this brings up a really crucial question. If resistors are the only ones that actually consume real power, turning it into heat or light, and inductors and capacitors are just borrowing and returning energy, what on earth happens in a real-world circuit where you have all three mixed together? Well, the answer lies in a concept that is absolutely essential in the world of electricity. It's called the power factor. And what it does is it helps us separate the power that's doing real, useful work from the power that's just kind of sloshing back and forth, not really accomplishing anything. And honestly, the best way to think about this is with a bag of chips. Seriously, the total power that the power company sends you is called apparent power. That's the entire bag of chips, air and all. Now, the chips you can actually eat, the good stuff, that's the active power. That's the power that's actually spinning a motor or lighting up your room. But then, There's all that air in the bag, right? That's the reactive power. It's necessary to create the magnetic fields for motors and stuff, but on its own, it does no real work. It's just air. So, the big takeaway here is that in any real-world AC circuit, the total power you're pulling from the wall is a mix of these two things. You've got the useful chip power, the active power, and then you've got this air power, the reactive power, which is just bouncing back and forth, taking up space on the wires without doing any heavy lifting. So, how do we measure how much chip versus air we have? That's where the power factor comes in. Think of it like an efficiency score, from 0 to 1. It's just the ratio of your useful active power to the total apparent power. A power factor of 1 is perfect. It means 100% of the power is useful chips. A power factor of, say, 0.7 means only 70% of the power you're drawing is doing any real work.
Okay, so why should any of us care about this? Well, a low power factor, which you get a lot with things like motors, is just plain inefficient. It means you have to pull more total power, more air, from the grid just to get the same amount of chips, or useful work. For big factories, this is a huge deal. The power companies can actually charge them more for having a low power factor because it puts more strain on the whole system. For you and me, it's simple. A higher power factor means you're getting more bang for your buck on your electricity bill.
So at the end of the day, the name of the game in electrical engineering is to get that power factor as close to a perfect 1 as you possibly can. The goal is to make sure that the useful power you're actually using is pretty much the same as the total power you're drawing from the grid.
But here's the final twist, the central paradox of it all. We call it wasted or useless power, right? But that reactive power, that air in the bag, is the very thing that's absolutely necessary to create the magnetic fields that make almost every motor and transformer in the world go. So while we're always chasing that perfect efficiency, that perfect power factor of 1, it leaves you with a final question to chew on. Could our modern world, with all its electric motors, even exist without this wasted power?